Hello. Today we'll be going over one of my favorite results from abstract algebra. And it's related to this theorem here. Okay, so this theorem first supposes that we have a field f and an irreducible polynomial p of x in the polynomial field f of x, right? Okay, if this is the case, then this extension field contains a root of this polynomial p of x, right? So this polynomial had no roots in f of x, but it will have roots in the extension field. Remember, this is the set of all congruence classes mod p of x in f of x. Okay, and one of my favorite applications of this theorem is about the complex numbers. And the complex numbers denoted by c here, right? I can make two arbitrary complex numbers, z and w, and right here I've just written out the familiar addition and multiplication rules for complex numbers, right? So z plus w will be a plus bi plus c plus di, and that simplifies to a plus c plus b plus di, right? So we have a new real part and a new imaginary part. Similarly, multiplication works out like this, right, when you FOIL everything out. And because I squared equals -1, this part here just becomes minus bd. So you get the new complex number ac minus bd, this is the real part, plus the complex, or the imaginary part, ad plus bc. Okay, so that's how arithmetic works in the complex numbers. Now, consider this extension field, which I've named K here. This is the extension field of R, the real numbers. Okay, and in R of x, x squared plus 1 is irreducible, right? Meaning there are no roots to this. No real number will make this polynomial equal to 0 if you plug it in for x, right? So this polynomial satisfies the conditions of this theorem, right? R is a field, the real numbers is a field, and this polynomial is irreducible in that polynomial field, right? Okay, so this theorem then says that this extension field should contain a root of x squared plus 1. All right, now remember, the elements of this set are all congruence classes mod x squared plus 1, right? So they're all essentially it means they can all be written as the remainders that you get when you divide some polynomial by this one, right? So the possible remainders that you can obtain. And by the division algorithm, those remainders must all have a degree less than this one, which means they're all either degree 1, degree 0, or they are equal to 0, right? So every element in this set can be written this way, right? As congruence class of R times congruence class of X plus congruence class of S, where R and S are just some real numbers. They could both be 0, or either one of them could be 0. Now, the congruence class of x, as it turns out, is the solution to x squared plus 1 in this extension field. The reason why is -1 is congruent to x squared, mod x squared plus 1. That could be readily verified. And then, because this is the case, because they're congruent, there's another result in abstract algebra which says that if these two are congruent like this, then their congruence classes must be the same. Okay, that means the congruence class of x squared, which is just this congruence class multiplied by itself, is equal to the congruence class of -1. Okay, so that means the congruence class of x is a solution. And here I've just renamed it alpha so that the notation just becomes a little bit easier to work with. Okay, so now, down here I've picked two arbitrary elements of this set, of the extension field, and you can see by adding them together, right, if we add these together and we follow the normal rules of congruence class arithmetic, right, this will eventually simplify like this, and then we could just write this as the congruence class of A plus C plus the congruence class of B plus D times alpha, which remember is our congruence class of x. And then similarly, I'm taking these same two arbitrary elements and multiplying them together using congruence class arithmetic. Congruence class of A times C gives me congruence class of AC, and then I'm going to get congruence class of AD times alpha, congruence class of BC times alpha, and then lastly, congruence class of BD alpha squared. But alpha squared, remember, is just equal to -1. So this simplifies to this next row where, you know, this term here just simplifies to this. Okay? And then finally, just combining like terms, really, we get this result at the bottom. Okay, now, notice the similarities between the arithmetic rules for this field and the complex numbers, right? They're completely identical. Z plus W, right? We get this result, A plus C plus B plus DI, and here we get this. Everything is exactly the same, except for the choice of symbols that we've used. Everything else works exactly the same way. So what that means is these two fields, the complex numbers and this field extension, are isomorphic. In other words, they're exactly the same except for the choice of symbols that you use. Using one is exactly the same as using another. They both have the same algebraic rules and everything. Okay. Now, this was a really profound result when it was first discovered. Nobody knew that this was going to happen. When people first started studying this stuff, the complex numbers were in use long before they made this discovery, and when it's just a really profound connection between different areas of mathematics that nobody really expected to be there. And this also has, well, one could make an argument for actually defining the complex numbers this way, because it's grounded in a theory that's sort of well established. When the complex numbers were first introduced, a lot of mathematicians reacted very negatively towards them. A lot of people had trouble accepting it because, well, is there really this number I which equals the square root of -1? It sort of seemed like people were just kind of making it up, right? But when you have this framework, you can see that everything is totally valid, and it works the exact same way that the complex numbers do. So yeah, this is a great example of some of the deep connections that you can discover between different branches of mathematics. Thank you for watching.